sklearn model selection. Description: the sklearn model selection module in scikit-learn provides a comprehensive set of tools for splitting, searching, and evaluating machine learning models. It allows you to efficiently prepare your data, tune your model's hyperparameters, and assess its performance. Inputs: dataset: a structured dataset containing features and labels for supervised learning or just features for unsupervised learning. Model: a machine learning model, e.g., linear regression, logistic regression, decision tree, etc., from scikit-learn or another compatible library. Outputs: model evaluation metrics, performance metrics like accuracy, precision, recall, F1 score, mean squared error, MSE, etc., depending on the task and chosen metric. Optimized model: the model with the best hyperparameter configuration found during the search process. Steps: data splitting, dividing the dataset into training and testing sets to evaluate the models. Generalization ability. Common techniques include train, test, split, simple division with a specified ratio, e.g., 80 training, 20 testing. K-fold cross-validation, dividing the data into K-folds, training on K1 folds and evaluating on the remaining fold, iterating through all possible combinations. Stratified K-fold cross-validation, similar to K-fold but ensuring that the distribution of classes is preserved in each fold. Hyperparameter tuning, finding the optimal values for model parameters that are not learned from the data, e.g., regularization strength. Number of trees in a random forest. Techniques include grid search, exhaustively trying all combinations of hyperparameters within a specified grid. Random search, randomly sampling hyperparameter values within a specified range. Bayesian optimization, utilizing a probabilistic model to efficiently explore the hyperparameter space. Metrics: accuracy, the proportion of correctly classified instances. Precision, the proportion of true positives among all predicted positives. Recall, the proportion of true positives among all actual positives. F1 score, the harmonic mean of precision and recall. Balancing both measures. Mean squared error, MSE, the average squared difference between predicted and actual values for regression tasks. Visualization plots. Learning curve plot showing the model's performance on training and validation sets as a function of training data size. This helps assess overfitting and underfitting. Validation curve plot showing the model's performance on a validation set as a function of a specific hyperparameter value. This aids in understanding the impact of hyperparameter changes. Fine-tune parameters. Test size specifies the proportion of data to be used for testing, e.g., 0.2 for 20. Random state, an integer used to seed the random number generator for reproducible results. N splits, the number of folds in cross-validation for K-fold and stratified K-fold. CV, the cross-validation strategy, e.g., K-fold, stratified K-fold, etc. Uncertainty methods. Bootstrap aggregation, bagging, combining predictions from multiple models trained on different subsets of the training data to reduce variance. Random forest, an ensemble method that builds multiple decision trees on random subsets of features and data, providing estimates of uncertainty. Challenges and fixes. Challenge 1: data leakage, information from the testing set might unintentionally be used during training, leading to overly optimistic performance estimates. Sample use case that resulted in challenge 1: using the entire dataset including the testing set to preprocess the data, e.g., calculating mean or standard deviation before splitting into training and testing sets. Fixes to challenge 1 ensure that any pre-processing steps are done only on the training data, not on the entire dataset. Challenge 2 overfitting the model learns the training data too well and fails to generalize to unseen data. Sample use case that resulted in challenge 2 using a complex model with a high number of parameters for a small dataset. Fixes to challenge 2 use cross-validation to detect overfitting and consider simplifying the model, reducing the number of features, or using regularization techniques. Challenge 3 computational cost tuning hyperparameters with grid search can be computationally expensive, especially for models with many parameters. Sample use case that resulted in challenge 3 performing a grid search over a large range of values for several hyperparameters. Fixes to challenge 3 use randomized search for more efficient hyperparameter exploration. Explore Bayesian optimization, or consider using more powerful hardware for faster computations.